for this skill, we're going to talk about fanouts, or I guess how to steal cable TV, and the trade-off that happens when you just put in a splitter and share the signal that way. So this is quite often basically what happens when you try to split a transmission line. So you have your transmission line coming in, and we'll just assume that, let's not worry about what the generator is. We'll just look at a very generic situation where we have a voltage coming in through this first cable, Z0, and this will be your splitter over here, and what you want to have is you want to have two transmission lines coming out. So over here you'll have one transmission line, and the wave that comes out of it we'll call V2 plus, and then over here going down you'll have this other transmission line, and the line coming out of it we'll call V3 plus. And usually we want to keep with the same type of transmission line, so let's just, for the sake of argument, just assume that they're all the same kind of transmission line with characteristic impedance Z0. And when we look at what happens, you're going to have a different reflective coefficient we'll just call gamma J, which is what we want to calculate. So basically what we want to find is the amount of power that will go into, the amount of voltage that will go into one line and the other line, or V2 plus and V3 plus, as well as the amount that's reflected. Let's take a look at what happens at the junction. So you have this wave, it's coming over this voltage, and then it sees this junction. Now remember, with transmission line theory, we don't have to draw what's on the other end, because at the moment that it reaches this junction, it doesn't see it. All it sees is more Z0, but now it sees these two Z0s in parallel. So at the junction to this V plus signal, V plus signal, it looks a little bit like this. You have your transmission line, and then coming out, you actually see a Z0 in parallel with Z0. So you see these two Z0s together. And note that Z0 parallel with Z0 is going to be equal to 1/2 Z0. So effectively what it sees is you have a Z0 and then you're terminating it with an impedance of 1/2 Z0. That's what it looks like at the moment it hits the junction. And so the reflection coefficient at the junction is going to be equal to new, which is 1/2 Z0, minus old, which is Z0, over 1/2 Z0 plus Z0, which is going to be equal to, all the Z0s cancel out, and you're going to find that it's equal to -1/3. So what that means is that the resulting reflected signal that would come out, so you would get a reflected signal that comes out, this V minus is going to be equal to gamma J V plus, or -1/3 V plus. And then you want to see what goes out V2 plus and V3 plus. So V2 plus in this case is going to be equal to, remember how we calculate the transmission, which is 1 plus the reflection. So 1 plus gamma J V plus, which is going to be equal to 2/3 V plus. And then the wave going out this way is also going to be 1 plus gamma J V plus, which is going to be equal to also 2/3 V plus. So in your bounce diagram, this is the amount that would continue to propagate over the two lines. And if you wanted to keep track of it, this is what would happen, as you would have these two waves coming out and you would continue to propagate from there. One nice little shortcut that we can also see here is the amount of power that's reflected. So if we wanted to calculate the power that's reflected, it's going to be, so the power in this negative wave going back through transmission line 1 is going to be equal to the voltage times the current. And remember, the current is going to be V minus over Z naught, right? Except for, yes, the minus sign. Someday I'm going to stop talking about this minus sign once we've had an exam and you've shown to me that you won't make that mistake. And so this will simplify into V minus squared over Z naught, which is going to be equal to minus, this is just going to be gamma J squared V plus squared over Z naught. So now let's clean this up a bit. You're going to see minus gamma J squared. And remember, V plus squared over Z naught is actually the incident power. So you can see that to relate the input power, the reflected power, to the incident power, unlike the voltage situation where you have this factor of gamma, in the case of the reflected power, the square of gamma tells you the amount of power that's going to be reflected, and that's because of the squared relationship between P and V. Now, continuing with the fan-out example, you can also do fan-out in series. So one example would look a little something like this, where you would have, let's say, in this example, a 10-volt source with ZG, which in this case is going to be 50 ohms. And then you send that through one transmission line, Z naught, we'll call that 50 ohms. And then here you have your transmission line 2, which is also 50 ohms. And here you'll have your first load, which is, we'll say 50 ohms, we'll just say it's perfectly matched. And the voltage here is V2L. And then here we'll connect the ground trace of these transmission lines to another transmission line. We'll call this Z03 is going to be, let's say this is a 100 ohm transmission line. And the load here is also going to be 100 ohms. So we won't have to worry about reflection. We just have to worry about, what the wave going across is. And in this case, we're going to define V3L as actually going in this way. So make sure you keep track of how the positive and negative terminals of these transmission lines are configured. Now, in this case, first of all, let's start by calculating the initial wave going in. So V plus or V in is going to be equal to V in, which is going to be equal to VG. And then again, you don't really care about what happens after the transmission line. You just see this 50 ohms. So you just see this Z0, we'll call this transmission line 1, over CG plus Z01, which is 10 volts over 50 over 50 plus 50, and you get this 5-volt signal going in. So now the question is, what are the voltages going here and here? And this is where the Thevenin equivalent model would allow us to think a little bit less hard, as long as we're careful. So remember the formula for the Thevenin equivalent model is, the idea is you know what the voltage is going in, and you want to be able to convert it into what everything else on the other end of this transmission line sees. And the formula, the procedure of how to do that is we pretend we have a generator where the value is equal to 2 times the input wave. So 2 times V plus, which is equal to 10 volts. And then that Thevenin equivalent source has an equivalent Thevenin equivalent source impedance of this value here, the transmission line value, so Z01, which is equal to 50 ohm. And then that's kind of how you would simulate at the output of that transmission line, so this junction over here. So let's draw out what the rest of this junction would look like for the wave as it exits this transmission line. So the wave as you know, this person standing here would see it. So what this person here, I'll just draw that over here as well for consistency. What this person will see is it will see this transmission line of 50 ohms. So that's going to be 50 ohms. And then this voltage is going to be V2L. So that's going to, whatever voltage you measure here, that's going to be the voltage that's going to go in this direction. So find that V2L, and that's going to be what the voltage wave going in that direction. And then separately, down here, you have a Z03, and you're measuring this V3L where the minus and plus is defined that way. And whatever V3L you calculate, that's going to be the wave going this way. And so let's just look at the circuit and see what it's going to end up being. So we can now look at the circuit and calculate that V2L is going to be equal to the voltage source, 2V plus, over this impedance, Z02, over Z01 plus Z02 plus Z03, which is going to be 10 over 50 over 50 plus 50 plus 100, and that's going to be 2.5 volts. Similarly, V3L, now remember, because this is inverted, we also have to add a negative sign. So it's going to be minus 2V plus, and then the voltage divider with Z3. So Z03 over Z01 plus Z02 plus Z03, which is going to be equal to minus 10, 100 over 50 plus 50 plus 100, which is going to be equal to minus 5 volts. And so that is going to be so this 5 volts here is going to be the value of the wave that goes that way, and this 2.5 volts here is going to be the value of the wave going this way. And if you had to do a bounce diagram, you would then track each of these separately, and same thing when they reflect back. Once they hit the junction, you would use a Thevenin equivalent circuit to figure out what the waves would be propagating into the other two transmission lines. So as you can see, this is matched because it gets hairy really quickly, but I think that the main thing to be able to keep track and make sure that you're able to do is to be able to convert this into the Thevenin equivalent and at least know the value of the wave that will launch into the other transmission lines.